Okay. All right, let's talk about the title of the lesson a little bit. Infinite, what does that mean? Never ending, forever. What does geometric mean? Multiply, divide. And what does series mean? Nope. What does series mean? It's your sum, right? So it's always asking for the total number of something like this. So this one is like geometric. We've done geometric series before. That was 1.4, easy peasy. The infinite adds a little bit to it. Okay, you have to be smarter than the formula though. Okay, so you guys have to be smarter than that. There's two types of infinite geometric series. There's convergent and there's divergent. The only one we can calculate for is the convergent. It's converging on, it's headed towards a number. And the fixed value that it's always headed towards, so if I start at 4 and then I go to 2 and then I go to 1, what's my common ratio here? Divided by 2, so we would list that as a 0.5, right? We're timesing it by a half. So we know these numbers are getting smaller. What's half of a quarter? What's half of a quarter? Half of a quarter? 1/8, right? What's half of an eighth? 1/16. What's half of a 16th? 1/32. So you guys see the pattern happening, right? So much easier to do as a fraction. What number is that getting closer and closer to? It's like an asymptote. Where are we approaching? 0. Those of you doing calculus with me next year, we're going to do limits of a function, and that's kind of what we're going to be looking at. What's happening to the x values when the y values are doing something else. Okay, so we can only use the formula on convergent series. So they're coming towards a number. Divergent is when they're headed to, what's happening here? We're timesing by 2 this time, right? 2 to 4 to 8 to 16, what's the next number? 32, what's the next number? Right, so where are we headed towards? Infinity. So Vishwa, if I asked you to count to infinity, could you do it?
It could take eternity.
Ah, I like that. So infinity is a concept, it's not an actual number, so you can't use it. So you can only use the formula on converging series. So those are things that are getting smaller and headed towards 0. So what does R have to be?
0.
Nope. What R is our common ratio? Because if it's less than 1, then what's happening to our numbers? They're getting smaller and smaller and smaller. So numbers less than 1, 0.5, right? Everybody with me there? Like I want a fraction. I actually want R to be less than 0, but less than 1, but greater than 0. Because on a number line, that's going to be all the numbers in there, which are decimal numbers, like 0.25, 0.3, that sort of thing. So that's the restriction on convergent series. If you have an R greater than 1, then your numbers are going to get bigger in size. They're going to be headed towards infinity. They're going to be headed towards positive infinity or negative infinity. And we don't want that. We want them headed towards 0. Okay, that's a lot of words. So, sum of infinity. T1 divided by 1 minus R. Again, so similar. R minus 1, 1 minus R. So similar. So take the time to actually consult your formula sheet before you use that. So sum, infinity, T1 1 minus r. The restriction on it isn't 0. I made a mistake there. That should be -1. So any value, so r has to be greater than -1, but less than +1. Can't be equal to, because if it's equal to the ones, there wouldn't be any change in the series. Like if I take 2 and I times it by 1, you just have 2, 2, 2, and that's not an increasing or decreasing. Okay, so S infinity is the infinite sum.
How do we have a number if it's infinite?
Because you are headed towards 0, and it's approximately. So it's taking all those numbers and getting really, really close. It's adding them all up because you're headed towards 0. That's the only time it will work. So T1 is the value of the first term. R is our common ratio. Remember, we can only use it on converging or not diverging, converging. So can I use the infinite formula here?
Yeah.
How do I know that? Just by looking at it, no math, how do I know it?
It's getting smaller.
The numbers are getting smaller, right? So we know that our R is decreasing. Can I use it here? No, numbers are getting bigger, right? So right away, I'm going to need to find the common ratio anyway, so let's take a minute and find the common ratio. So I'm going to take -1/3, and I'm going to divide it by 1. What do I get? -1/3. Good job, everybody. Is that on the number line between -1 and +1? Does it fit on that? Yeah, so we know it is a convergent series. So we can use the formula with a convergent series. Okay, let's go to this one. I need to find my common ratio, so I'm going to take -4. I'm going to divide it by 2. R is equal to -2. Does it fit on that boundary, that number line, -2? No. So this is divergent. And I can't find a formula for that. Or I can't find a sum for that one. So the only one I can work, yeah?
Could you write the sum of E infinity?
Yes, you could. You could. You could write the sum as an infinite. Because we don't know what it would be. But that's not super helpful.
Yeah.
So we just usually don't do it on that one. But you're not wrong by saying it's infinite. Okay, yep.
Is divergence like a no solution situation?
Yeah, kind of like a no solution or an infinite number. Infinity is my solution, which isn't.
Yeah.
I said, oh, you got infinity on your test.
Yeah.
Right? Like, not super helpful. So let's just dump this into the formula. T1 is 1. And then we have R, no, we have 1 minus R. I did a lot of math there and I didn't show you any steps. So when I have a negative sign, they turn into add the opposite, right? And when I add fractions, what do I need? Common denominator. So that full value of 1 turns into a 3/3. And so I'm going to have 4/3 here. So this is really like saying 1 divided by 4/3. We're going to go 1 times the reciprocal. So I kind of expect you to know how to deal with fractions. Sometimes you'll show your work, sometimes you won't. Whatever makes the most sense to you. Just make sure you know what you're doing. Okay, pretty picture. Oh, this is really, if I turn that on, is that better? Not really. Okay, so this is a gray piece here. It's hard to see in mine, but you guys can see that it's gray. These are the black squares. And each, assume that the black square represents a quarter of the largest square. So that's square 1. And then this part here represents a quarter of it. That section right there represents a quarter of it. Okay?
But there's more than one black square.
Right, so then this is a quarter of this square here. And then this one is a quarter of that square there. And that one right there is a quarter of that tiny square. So it keeps going on. It's like an echo. Write a series of terms that would represent this situation. How many squares am I starting with here? The big one. So that would be 1. And then what's next? What does the black represent? 1/4. And then this is a quarter of a quarter. So how much is that? Quarter of a quarter. Mm-hmm. And then I got a quarter of a 16th. 1/64th, right? Okay. So, what's my common ratio? 1/4. How much of the total area of the entire square, so the big one, square 1, is shaded? Can I use the sum, the infinite sum here? Yes, because my common ratio fits into the boundary of -1 to +1, right? So I know I can use it. Okay, so you guys go ahead and calculate it. Find the infinite sum. Okay, let's see how good you are at your fraction work. You good? Brilliant. So how will you know if you use an infinite sum or an infinite geometric sum or a geometric sum? You're going to look for the words goes on forever, pattern continues infinitely. Right? So you're going to look for words that mean it goes on forever and ever and ever. Okay. I don't love this question. You know what? It's a Tuesday. I'm not going to do the last example, and you're going to cut number 2 from your assignment.